Okay, so the last segment in this series on bifurcation theory is I want to give the conditions for each bifurcation and mention the variants that occur. So let's go through each one in turn. So first of all, the saddle node. So this is a case where if we draw the curve here of x, that these are going to be a curve of fixed points against mu, that the fixed points exist up to a certain mu, and then which we'll call mu naught, and then after that they cease to exist. So how do you know that this kind of thing is going to happen, or what's going on in terms of the stability and so on of this? So the idea is that usually what we would see here is that the curve here on the top maybe consists of attracting fixed points, and then the one on the bottom consists of unstable fixed points. So if we look in terms of the eigenvalues of the Jacobian, the way we might think of this is that in the attracting case, perhaps here all the eigenvalues then, well, this is true, in the attracting case will be in the left half plane, and this is the lambda in C. This is the set of eigenvalues of the Jacobian evaluated at the fixed point in question. There may be loads of them, there may be just one, depending on the dimension of the underlying phase space. And then in the unstable case, what's happened here is that this eigenvalue, as we sort of imagine kind of moving around here like this, going along and then turning the corner like that, if we can sort of imagine that in this direction, and I don't mean these arrows dynamically, that's why I'm drawing sort of double arrows. I mean, they would just imagine following this curve here. And as you follow the curve, you will see the eigenvalues change for the linearization, and that what you will see as you go from the attracting to the unstable case is that an eigenvalue has gone through zero. So right here at the bifurcation point, at the saddle node point, what you would have is an eigenvalue right at zero. So the key is that having an eigenvalue at zero indicates a bifurcation here. So an eigenvalue right at lambda equals 0 indicates a bifurcation. But this is the structure of the nature of the fixed points in the x mu space that sort of tells us that it's this type of saddle node bifurcation. Because if I now go on and talk about the x bifurcation, say the transcritical bifurcation, right? So in this case, we're having the collision of two curves of fixed points like this. This is in x mu space, and you actually see exactly the same structure in terms of the eigenvalues. So imagine you're sort of moving along here like this, right? Again, this is not dynamic. This just means that I'm imagining, thinking about the structure of the linearization of the fixed points as evaluated at the relevant fixed points here, right? And perhaps this is attracting here, right? Which means that there are eigenvalues in the left half plane. Then what you will see is that this is, after it's crossed the other critical point, is actually unstable. These again are in the sort of spectral plane here, and at the bifurcation point here you have an eigenvalue going through 0. So now imagine that I'm actually going along this curve here, the other one. So what's happening here is that you would be doing the opposite. So you would be going from here, unstable, here, and then up to here afterwards to the attracting case here. So in this case the eigenvalue has gone through, so let's call this curve B and this curve A. So under A, what's happened is there's an eigenvalue that has gone through 0 from the left to the right, and under B, sort of the opposite has happened. There's an eigenvalue that has gone from the right to the left. So again, what you need to do is to understand the structure of the fixed points in the phase space and understand what's happening with the eigenvalues. But again, the bifurcation point corresponds to eigenvalue going through 0. Eigenvalue at lambda is equal to 0.